Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultrafast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays.
Convective storms hold an extraordinary surprise. Under just the right conditions, they fire off some of the highest energy light naturally found on Earth, terrestrial gamma-ray flashes, or TGFs. Rising and falling snow and ice particles repeatedly collide, filling the cloud with electrical charge. Once the electric field is strong enough, a current flows and a lightning flash occurs. The flash produces an abrupt reconfiguration of the electric field. In some cases, a surge of electrons rushes toward the upper part of the storm at speeds nearly as fast as light. When deflected by air molecules, these accelerated electrons give off gamma rays, producing a TGF. Data from NASA's Fermi Gamma Ray Space Telescope suggest more than 1,000 TGFs occur each day all over the globe. For the first time, improved data link dozens of TGFs to specific tropical weather systems. Tropical storms far from land tend to generate less frequent lightning. Nevertheless, observations show they are surprisingly prolific producers of TGFs. Tropical storm Manuel made landfall just shy of hurricane strength. As it rapidly weakened, it produced 2 TGFs within 24 hours. More typically, TGFs are associated with the strengthening phase of a storm. As Typhoon Bolivan rapidly developed in 2012, thunderstorms nearly 500 miles from its center launched a TGF with 4 distinct pulses. So far, the record holder for TGFs is the rapidly strengthening tropical wave that later gave birth to Hurricane Julio. It produced 4 TGFs within 100 minutes. A 5th followed the next day, with nothing further. What scientists learned so far is that weaker tropical storms are capable of producing more TGFs, and those events can arise anywhere in the storm. For stronger storms, like hurricanes and typhoons, TGFs are more common in the outer rain bands, which host the highest lightning flash rates in these storms. The findings provide new insights into the relationship between storm intensity, lightning frequency, and TGFs. This adds another important piece to the puzzle of our understanding of TGFs and how they are created in thunderstorms, the most powerful natural particle accelerators on planet Earth.
Terrestrial gamma ray flashes, or TGFs for short. Studies by NASA's Fermi Gamma Ray Space Telescope have shown that TGFs fire up about 1,100 times a day. Now, new research combines Fermi detections with ground-based radar and lightning location data. These studies show that TGFs come from more diverse types of storms than previously thought. In a thunderstorm, collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash. All lightning produces a strong and sudden change in the storm's electric field, but the upward portion of an intra-cloud flash sometimes sends a surge of electrons rushing toward the upper part of the storm. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when their paths are deflected by air molecules. Using global lightning location networks, scientists can determine the TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding, TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too.
So the atmosphere is largely neutral. So you need some energy somehow to break the electrons and away from the neutral atom or molecule. And the way the ionosphere is formed is largely through the extreme ultraviolet radiation coming from the sun. That provides the energy by which you can separate electrons from the atom, and they become free electrons. That atom now becomes positively charged, which is an ion, and that makes up the charged part of the ionosphere, largely from the solar extreme ultraviolet radiation. As we get deeper into the atmosphere, that radiation, it gets absorbed by the upper part of the atmosphere and doesn't reach the surface. You need more energetic particles to further ionize the atmosphere as you get closer to the surface. That's partly brought on by galactic cosmic rays. They have very high energies that can get through the atmosphere, and in that path have a lot of energy, collide with neutral particles and create ionization that way. There's also energetic particles from the magnetosphere that come in, and they also create collisions and create ions in the lower atmosphere. And then finally, at the surface, you have radioactive decay when one outcome is radon. And that radon will come up and emanate from the surface and create charged particles. So the distribution from the surface all the way to the edge of space is variable, but it's this distribution that is so challenging because there's chemistry and there's physical pathways and there's external sources and forces that make it very difficult for us to account for it all. But we know those ions constitute the conductivity of the atmosphere.
This is the Endurance rocket ship, and she's about to discover something incredible and fundamental about the Earth. So why here? What makes Earth this special place that we all call home? one of the reasons may be due to the energy fields that our planet creates.